This tells you the background of our research. We want to study how much is the relevant blade containment. For example, for the compressor, if we have a burst strike and one of the blades of the engine is released, it could penetrate in the fuselage and kill people. Instead, for the turbine, the fatigue could occur and part of the turbine could be released and again penetrate in the fuselage, and the results are often catastrophic. For example, here for the Delta Airlines flight 1288, the impact left 2 people dead and 2 several injured. And to achieve our research, we need a material model input deck that accurately predict the material behavior in impact test material simulation. Full-scale tests are usually made, but they are very expensive, and for this reason, we want to switch to simulation. So, to get the material model right, the first step is to have a predictive simulation. Here we compare 3 material models. And for the simplest one, MAT24, which is an elastoplastic material with an arbitrary stress versus strain curve and arbitrary strain rate dependencies can be defined, but it doesn't have temperature-dependent hardening, strain rate-dependent failure, temperature-dependent failure, at 3D state of stress failure surface. Another popular material, MAT15, it has more capability. In fact, the failure surface depends on the triaxiality and can be tuned to a single failure condition, but it cannot predict the mode of failure. So for this reason, we move on MAT24 material model. It resembles to the original Johnson-Cook material MAT15, but with the possibility of general tabulated input parameters. It means that it has more capability than the other ones, and it can fit more material, and it allows more accurate prediction in material behavior. So, this one is the MAT24 input deck. I want to show you just some key points. So starting on the left, we have LCK1 is the strain rate sensitive table. It defines effective stress as a function of effective plastic strain for each temperature, for each rate, sorry. LCKT is the temperature sensitive table, and it defines the quasi-static effective stress versus effective plastic strain for that temperature. The third one, LCF, defines for each load parameter a load curve giving the plastic failure strain versus triaxiality. Instead, the last 3 curves are defined plastic failure, strain, but LCG as a function of plastic strain rate, LCH as a function of temperature, and the last one, LCI, as a function of element size. To obtain all these curves, we have to do material tests, and Ohio State University made a lot of tests. And so we get a half-inch titanium plate designed with this specimen, and the reason of this shape is because we want to capture the 3D failure surface, and for different shape of specimen and test type, the material will fail at different stress triaxiality and loading parameter. And for this reason, we can catch a lot of points on the failure surface. So, starting from the material test, we develop all the input curves to achieve a single MAT224 material model that is able to match all the force test displacement and also the DIC image for each type of test. And so these are the results. Here we have a tension test, punch test, compression test, and torsion test. So to test the ability of MAT224 material model, we compare the ballistic impact test result with the ballistic impact simulation result. And NASA tested 4 different plate thicknesses for the impact test, and we have exactly simulated this geometry. So our 0.5 inch, half inch, quarter inch, 0.14 inch, and 0.09 inch. And the half-inch plate impact test is the same used in the material test. And based on that, we developed the MAT224 material model. But for all the other thicknesses, we always use the MAT224 material model based on half-inch material test. Here is the simulation material summary for the half-inch and quarter-inch plate. The projectile used is made of A2 tool steel, so we use matte elastic to describe its behavior. Because A2 tool steel is a hard material, and the plastic deformation after the impact is negligible. Instead, for 0.14 inch plate and 0.09 inch plate, the material of the projectile used was annealed titanium, and the plastic deformation is not negligible anymore. And so we use matte piecewise linear plasticity. And we get the material property from literature. Instead, for the plate material, it doesn't matter which the thickness is, because we always use MAT224 developed from half-inch plate. So here you can see the material input deck used to the projectile, for the projectile, and is the difference for half-inch, quarter-inch, and for 0.09 inch and 0.14 inch. And here we have a comparison of the deformation after the impact, just for the 0.14 inch plate impact test, where we match the plastic deformation pretty well. So once again, I want to emphasize that identical plate was used in ballistic impact test, as well as to develop the material failure model. So this chart shows the 0.5 inch plate test and simulation result. We have the exit velocity as a function of initial velocities, the impact velocity. And we can see how the ballistic limit match very well the curve, match very well, and the curves trend are very close between test and simulation. Furthermore, we compare the deformation contour between test and simulation, and we also compare the plug-in shape, which is not identical, but it's similar. So now we move on the quarter-inch plate. There are some material tests done to tell the differences between these two materials. And we can see that the same colors means strain rate, same strain rate, and all the solid lines refers to half inch plate, and all the dashed line refers to the quarter-inch plate. We can see that the half-inch plate is stronger than the quarter-inch plate. So the quarter-inch plate will be simulated with the material model that is based on half-inch plate. So given that we don't expect a particularly good prediction, in the simulation where we use a mismatch material model, since the half-inch plate, the 0.5-inch plate, is stronger than 0.25-inch plate, which means that the half-inch material model is stronger than the 0.25-inch material model. So we are expecting that the predictive simulation ballistic limit to be higher than the actual test ballistic limit. And here, how you can see here. But I want to tell you another things here. So the quarter-inch curve is not just scaled down, but it is flatter than the half-inch curve. Because it is flatter, the necking point comes early, and because it is flatter, you have more localization. So in the neck, we develop so much higher strain. It means that the failure strain that you have to specify in the failure surface is not necessarily smaller for a quarter-inch than half-inch plate. So this is the test and simulation result. And always in terms of exit velocity as a function of initial velocity. And we don't have a good match. And one of the reasons is the difference between the material model that we used to develop MAT224 and the material used in the impact test. So basically, in the continuous mechanics sense, they are different materials. In this special case is shown a containment test, and we have a comparison between the plug shape obtained in the test and in the simulation. But in the test we have a strike plug shape, whereas in the simulation we have a cone plug shape. So they are not very close. Now we move on the other thickness. And here we have the material comparison for the 0.14-inch plate and a half-inch plate. And if you look the pink dash line curve, that it refers to 0.14-inch plate is lower than the pink solid line curve that it refers to 0.5-inch plate. But it is more ducted. But the trend is not consistent looking the green line that is a higher strain rate. It looks like a different material. And unfortunately, we don't have quasi-static test for 0.14-inch plate. But I want to highlight that in all this material, you have a trend where the higher the temperature is, the later you go to fade. And the higher is the strain rate, earlier you go to fade. But unfortunately, if you increase the strain rate, you also increase the temperature. So you always have both the effects that simultaneously come in and fight each other. Which one is going to be dominant? It's just a lot of tests is the answer. These are the result. It's always exit velocity as a function of initial velocity, and the simulation still overestimates the ballistic limit. It means it means that it overestimates the strength of 0.14-inch plate. The fact that we are modeling the plate with a material model that is stronger than the actual plate, it means that our ballistic limit prediction should be higher than the test, as it was in a quarter-inch plate that I showed you before. Okay. You can see the picture on the left shows the failure mode for the simulation with the highest containment velocity without plug, because we wanted to match that kind of test, and we completely miss the failure mode. So simulation does not predict the fracture failure as in the test. So we move on the last plate. And again, I show you the material comparison between 0.09-inch plate and 0.5-inch plate. We can see that even in this case, 0.5-inch plate is stronger than 0.09-inch plate. Unfortunately, there are no quasi-static data for the 0.09-inch plate, so we can just compare the pink line and the green line, which are at high strain rate. Instead, the light blue line shows the true stress versus true strain for the annealed titanium projectile, where we have used map 20 to model it, and then it's like boxing the line. Then it's weaker than the plate material. So once again, I want to say that the material model based on 0.5-inch plate is stronger than 0.09-inch plate. So based purely on that, we would expect that predicted ballistic limit to be also higher than the test. However, in this case, the simulate prediction, you can see here, is actually lower, and the test than the test. And the predictive failure mode is not a good match at all. So using the 0.5-inch plate to predict the 0.09 titanium plate is not particularly good. Just to be clear, I mean, it's not that the ballistic limit is off by 100%, but it is in wrong direction of mechanical properties. So here we have the simulation result. It is always exit velocity as a function of initial velocity, and how you can see the simulation underestimates the ballistic limit, which means that the simulation underestimates the 0.09-inch plate strength. And the reason is different failure mode between test and simulation. So in the figure on the right, you can see a fracture failure mode, and when fracture occurs, there is more material involved in the failure, which means that more energy is absorbed by the plate. And our simulation doesn't predict the fracture very well, and for this reason, the ballistic limit it is lower in our simulation. Furthermore, the experimental curve just for the 0.09-inch plate, it doesn't follow the trend that we are expecting from analytical formula. So we can see that the test failure mode compared with the simulation, and on the top we have a low velocity, and at the low velocity the failure is predominant by fracture mode. And in the simulation, we don't predict the same tearing fracture mode. And this is the reason of underestimate ballistic limit. You just look out that the test and the simulation shown have two different initial velocity, because we want to compare the fracture mode for a contained case, and using the same velocity, it wasn't possible. So instead, at high velocity, we have the same straight plug shape. So this one is the last slide. It's a summary. I mean, of course, the half-inch titanium material model MAT224 works very well for the material test, as we have shown in the first slide. Furthermore, we have a good correlation with force displacement and DIC match, thus good strain match. Instead, for the impact test, the MAT224 developed, it works very well for the half-inch plate, even if the failure mode is not quite right, but it is marginally good for the other thicknesses. So, when material model match the actual material properties, correlation is excellent. And material process control is very important to maintain a narrow production range of properties in order for certification by analysis to provide predictive result across a production lot of material. Thank you for your attention and question and comment.
We do have time for maybe one question, if there are any questions.
Can you go to slide 23?
Yeah.
So I'm curious as to why, with the simulation, you get cases where you get quite a big difference in impact velocity, the same exit velocity.
You mean here?
No.
Here?
Right there.
Yeah, there.
Because all these tests have an impact angle. So what's happened, when the impact angle is higher, you have a lower exit velocity, like in this case.
So it is quite sensitive.
Yeah, a lot. I mean, it's very sensitive. Yeah. So. Yeah.
Okay, thanks again. If you have any other questions, you can follow up with the Stefano app.
Super.